Okay, so welcome to AIAA New England Zoom session tonight. Our speaker tonight is Dr. Jim Kuchar from MIT Lincoln Lab, speaking on the topic of a history of airborne collision avoidance system technology. Dr. Kuchar is an assistant head of the Homeland Protection and Air Traffic Control Division at MIT Lincoln Lab. He received SP, SM, and PhD degrees in Aeronautics and Astronautics from MIT, focused on flight deck alerting system displays, algorithms, and risk analysis methods. Jim served on MIT's faculty from 1995 to 2003, after which he joined Lincoln Lab, leading development of collision avoidance system technologies for manned and unmanned aircrafts. In 2009, he transitioned into managing Lincoln's portfolio of weather air traffic management programs and moved into his current role overseeing the laboratory's air traffic control mission area in 2019. Jim is a private pilot and has authored and co-authored over 110 reports, including 70 referred journals and conference papers. He is an AIAA Associate Fellow, chair of the National Airspace System Operations panel of the FAA's Research, Engineering and Development Advisory Committee, or REDAC, and associate editor for AIAA Journal of Air Transportation. Without further ado, Dr. Kuchar. Yeah.
All right, great. Yeah, thank you very much, Hiro, for the introduction there. Yeah, so I'm really happy to have this opportunity to provide a little bit of a historical overview of the development of collision avoidance technology, which is really, I think, an amazing success story in aerospace engineering. So hopefully you'll enjoy the little history here and learn a little bit more about this great technology. I do want to thank a lot of the presentation here. I didn't develop myself. Most of it I didn't develop myself. It's really been built upon by many colleagues at Lincoln Laboratory and other organizations as well. So I really want to thank them for all their work as well. I see several of them are on the webinar as well. So without further ado, first, just want to start. Obviously, a mid-air collision is one of the most horrible accidents you can envision in air transportation. So we obviously want to prevent them as much as possible. And the good news is that mid-air collisions today are extremely rare. This plot is showing in sort of the teal color the growth in air traffic since 1970. So we have about 8 times more flights today or in 2019 than there were in 1970. So there's been a huge increase in the number of flights worldwide that are being flown. And at the same time, the blue line, the jaggedy blue line here is the rate of mid-air collisions that have been happening with a 10-year sliding window. So you can see there was a significantly higher risk of mid-air collision back in 1970 compared to today. In fact, it's come down by a factor of 30 over those decades. So if we were flying today with the level of safety of 1970, we would be seeing about 7 mid-air collisions a year around the world. And thankfully, that's not happening. In fact, the risk now is somewhere around 1 in 300 million flight hours, which is really quite an exceptional safety record. And it's due to a number of technologies in air traffic control, one of which is collision avoidance. So it's certainly a piece of the solution here. And if we go back to the earlier years, in the 1950s, for example, there was a very bad mid-air collision over the Grand Canyon, 2 flights flying from the West Coast to the East Coast. And at the time, the technology for separating aircraft was very procedural. Aircraft were given altitudes and routes to fly. They periodically would call in on the radio to report their position. And in best case, there was somebody moving a little marker on a map to sort of see where the planes are and maybe give some changes in their trajectory if necessary. And obviously, that doesn't hold up very well in the long term with a lot of traffic. And so this mid-air collision really raised awareness in the country that there needed to be a more complete air traffic control system. And in fact, that led to the establishment of the FAA. This is one of the precipitating events that got the FAA started. And you know, coming from the FAA, then a number of air traffic control technologies followed. And so there were radar systems deployed, air traffic control systems deployed, but unfortunately, accidents still continued to happen. And these are two more very important collisions that happened in the 1970s and 80s with air traffic control, with radar. These were aircraft flying under air traffic control services, with good radar coverage, and yet accidents were still happening. And so this again raised additional awareness that there needed to be yet more protection for this type of an accident. And so there was a congressional mandate for an independent collision avoidance system to be installed on large aircraft by the mid-1990s. And so that led to the airborne collision avoidance technology that I'll be talking about today. So the idea here is that there's a system on aircraft that independently surveils other aircraft nearby. And if there's some sort of failure in the larger system, maybe there's a failure of an air traffic control radar, or a human error where either an air traffic controller or a pilot gives the wrong instructions or does the wrong thing, or they can't see out the window to avoid another airplane just by looking out the window. This system will sort of be that last safety net to provide some protection and prevent an accident. So that led to what's called the Traffic Alert and Collision Avoidance System, or TCAS, I'll be calling it. And again, it's part of a layered protection scheme. So this diagram on the bottom is sort of showing those different layers. So in the green, you have sort of procedures and the structure of airspace that's been set up since the early days of aviation. That's what was in place in the 1950s, basically, that aircraft fly given routes and have certain altitude separation that provides some level of protection. And when necessary, air traffic controllers are monitoring the traffic. They may provide directions to the pilots to change heading or altitude or speed to maintain separation. And the goal there is to keep aircraft well separated, typically 3 or 5 miles apart. So there's a lot of space between them and a good safety margin. And for the vast majority of time, that's sufficient to keep aircraft safely separated. But should there be some sort of issue where aircraft do get close, that's where TCAS comes in. And TCAS itself provides 2 layers. There's what's called a traffic advisory, or TA, which about 45 seconds before a collision would happen, issues a visual indication in the cockpit and also says traffic. And the intent there is to make the pilot aware that there's another airplane nearby. They can, if the weather's nice, they can look out the window and try to find that traffic and make sure that things are going okay in terms of staying separated. And it also just serves as sort of a get ready cue that if things continue to get worse, they might be given an avoidance maneuver advisory to actually do something with the airplane to avoid a collision. And that happens about 15 to 35 seconds before a collision with what's called a resolution advisory, or RA. And this would be telling the pilot to climb or descend typically. And the pilots are trained to do what that system says, because it knows sort of with the best surveillance, with only a few seconds left maybe to save the airplane, what you need to do. And the other aspect of TCAS that was built in is that it's coordinated, so that if 2 aircraft have TCAS, if one climbs, the other airplane will descend, so that they're not both doing the same thing. Obviously, that's an important consideration. So there's sort of a few main components to TCAS. There's a surveillance component, which is obviously needed to know where the other airplanes are and track them over time. So there's technology that was developed to perform that, detecting intruders, what we're calling intruders are just other aircraft, and track them over time. There's a set of algorithms that then use that information to decide, first of all, does the system need to do something? Do they need to bring the airplanes, the intruder, to the attention of the pilot? If they do, what should they tell the pilot to do? Should it be a climb or descent? And then to coordinate that with the other airplane, if the other airplane also has TCAS, like I said. And then the third component is the display in the flight deck. There's typically a traffic display and then some other display that tells the pilot what to do, whether to climb or descend. And I'll show an example of how that works in a minute. So So this is a system that was decades in the making. In fact, development of a collision avoidance system began well before the mandate for it, primarily through cooperative work between Lincoln Laboratory, MITRE Corporation, and the FAA and several airlines. And as you can see, starting in the 1970s and 80s, there was work in building the surveillance technology and building the algorithms that would provide that collision avoidance information. There have been several updates to that system. The first system deployed was called version 6.04a, and then there was a version 7 and 7.1. And most recently, there's a version of collision avoidance called ACAS X that I'll talk about towards the end of the presentation today. And I'll be talking a little bit else also about some of the other work that was going on in terms of, obviously there needed to be some, both in terms of modeling and simulation to build the system, and then flight testing to demonstrate that the system in real life operated, under the assumptions or with the same performance as had been assumed in some of the models. And then there's additional work in coordinating the maneuvers through the data link, assessing how well the system's working in operations, and making some additional improvements in the surveillance technology. So, but as you can see, it took a relatively long time to develop TCAS initially, and that's in part due to the fact that there wasn't much data to build models on at the time, and also somewhat limited computational capability. So it took a great effort to put together the physical models for how the system might operate, and then to validate it through a number of computer simulations to make sure that the system was going to operate properly. So I'll talk a little bit about first the surveillance component, and I'm going to just touch on a few parts of this. But TCAS is based on the same surveillance technology as the rest of the air traffic control system is built on, or was built on at the time, using transponders on the aircraft to help provide additional information to radars or other aircraft. So what you see in this radar in the picture here, the bottom part, the red parabolic dish, that's a primary radar that would reflect energy off of an aircraft's skin and determine range and azimuth using primary radar. And the transponder system uses this flat panel array on top of that radar, which is a beacon interrogator. So it turns with the primary radar, but it's actually sending out its own signal at 1030 megahertz with a particular code, which is shown by these little blips here in terms of the timing of these pulses. And the aircraft are equipped with transponders, which when they receive that interrogation code, depending on what form it is, whether it's this sort of short interrogation or this longer one, will send a reply message at 1090 megahertz encoded either with the identification code for that airplane, which has been assigned, or with the aircraft's altitude. So the interrogator can, as it sweeps around, it's sending out these interrogation pulses, and the aircraft are replying with their identity and their altitudes, and then that's what appears on the air traffic controller screen. That system has worked well. It's been in place for several decades, called ATCRABS, Air Traffic Control Radar Beacon System. But a couple limitations. One is it only supports that 4-digit code, and it's a octal code. So it's actually, there's only 4,096 different unique identities, and some of those are reserved for special uses. 4,096 sounds like a lot, but once you start getting a lot of airplane flying around, you don't want to have them changing their codes all the time. You quickly run out of those numbers. So that's an issue. And then another issue with ATCRABS is that it makes it more difficult to keep the reply messages separated. And here's just a little cartoon showing a radar as it's going around, and maybe there's two airplanes that are at roughly the same distance away from the radar. And so an interrogation pulse is sent out, both transponders receive that and send replies, but the replies are overlapping because the airplanes are just sort of blindly sending this reply back. And it makes it very difficult to separate out those responses. Now, there's actually been some really interesting work done to sort of extract as much as you can out of those overlapping messages, which I won't get into, but It's one of the challenges with that initial beacon system called ACAS is that you have these overlapping messages potentially that make it more difficult to track aircraft. So one of the technology improvements that was done was to develop what's called the mode select or mode S transponder system, which uses the same frequencies and the same basic waveforms and interrogations, and it's backward compatible with ATCRABs. But the interrogation message is a little different. It encodes a particular aircraft's identity so that you can interrogate specific aircraft now, and just that airplane, when it receives that code, knows that it's going to reply. And if a transponder receives some other airplane's code, it doesn't reply. And instead of 4096 different codes, this uses a 24-bit ID, which is many more times larger. Each airplane has a unique code. It's basically built into the transponder what its ID code is. So every plane in the world has a different 24-bit ID. And that allows a radar to, like I said, sort of once it knows who's out there, it can then interrogate airplane A and then schedule an interrogation for airplane B. And the radar technology is smart enough to sort of space those interrogations out so that the replies won't be overlapping. And so that's the really the fundamental technology here that allows radars to track different aircraft reliably and get data from them, from each aircraft uniquely. So, so when we get to TCAS, so here's sort of a rough schematic. The airplane has a transponder, and it's also got a separate TCAS unit, which is this collision avoidance system that has its own antenna. And what TCAS does is it sends out its own interrogation, just like it was a radar on the ground, except this is on the airplane. So once a second, it's sending out an interrogation. The other airplanes around that have transponders reply to those interrogations. And the TCAS unit is measuring the range using just the round trip time of the message. It's got a directional antenna that provides an indication of roughly where in azimuth the intruder airplane is. And it's getting the altitude of the other airplane through that encoded message reply. If it's what's called mode C or mode S, it's got the altitude included in that message. So what you could then do is start to show on like a traffic display. So this is sort of a top-down view. Here's your own airplane. And this yellow circle is showing where this intruder airplane is relative to me. So it's at about the 2 o'clock position. It's so many miles away. And this plus 08 means it's 800 feet above me and descending. And we get the descent rate by tracking over time how the altitude is changing. So that's basically how TCAS works in its surveillance. So again, it's independent of ground radars. It does it all by itself on the aircraft. It will detect and track airplanes automatically that are flying around. And if there is a resolution advisory, it also sends out this coordination message so that if the plane on the left is indicating it needs to climb, that message goes over to the airplane on the right and says, whatever you do, don't climb because I'm climbing. And there's a tiebreaker there. If both systems for some reason give the same answer at the same time, there's a tiebreaker based on their 24-bit ID. Basically, whoever has the lower ID number gets to win that tie, and the other airplane will reverse its sense to stay compatible. So this is just a picture of some of the early flight testing that was done at Lincoln Laboratory. They put, just basically a 4-element array on top of the airplane that provides that directionality for the tracking of targets. And on board the aircraft, you can see the electronics they had to sort of collect that data. And the great value of doing these flight tests was to validate the modeling that had been done in terms of how this antenna was going to perform under a variety of different traffic and clutter conditions. So it was very important towards the development of the system. So I'll just show an example of how this works. So this is running a little animation here. We've got 2 planes coming. And again, as you can see here, this jet airplane is this little cross. This other airplane is 200 feet below us. It's about our 11 o'clock position and getting closer. And I don't have the sound turned on, but when it gets about 48 seconds away or so, again, TCAS is tracking that and says, hey, you're getting a little close here. I'm going to warn the pilots about this other traffic. And so it says traffic, traffic. The symbol turns to a yellow circle to help highlight that. And at this point, the pilot then can start looking out the window or start asking air traffic control what's going on, or just be ready to do something if things get worse. And if things do continue to sort of degrade as the planes get closer together, the system continues to track, and at some point it decides that this is getting too close, and it issues this resolution advisory. In this case, it's saying climb, climb, and this display has sort of two aspects to it. It's a very complicated display in some ways. It is showing not only sort of a top-down view of where the traffic is, but then this dial on the outside is the vertical speed indicator. So this arrow is indicating whether the aircraft is climbing or descending. Right now we're level. And what this red arc is telling the pilot is that they need to increase their climb rate until they get to the green. So basically to 1,500 feet per minute or more. So the pilot would start, disconnect the autopilot and pull back on the yoke and then start to climb. And you can see the vertical speed starting to increase. As the plane climbs, the other airplane is getting farther below. So that's a good sign. It's now 500 feet below. And when it gets far enough away, the system says, okay, we've gotten enough separation now, things are safe, and you can return back to level flight. And then once you actually start to increase in range, the system says, okay, now the situation is cleared and you can go on back to your original clearance and fly along. So that's basically how the system operates. And then internally what's going on is TCAS is a little simplification here, but it's basically doing a straight line projection based on what the system knows about what your own airplane is doing and what it's finding out from this tracked airplane. So it projects ahead in time and looks to see where along those straight lines, where those planes are going to be closest and how far apart are they going to be vertically. And if that's a small enough misdistance that the planes are going to be too close, then it runs another algorithm to basically look and see should we climb or descend to avoid this threat. And that model assumes it's going to take about 5 seconds for the pilot to react to the resolution advisory and then climb to that 1,500 foot per minute climb or descent rate. And the system will select the sense, climbing or descending, that gives the most separation. So in this case, it looks like a climb would be better than descending. And then it will actually evaluate a few different alternatives to see if maybe something a little bit less aggressive is still sufficient. So it will look at not just climbing, but maybe what if it just tells the plane to not descend or not descend faster than a certain rate? And it will sort of evaluate those against some minimum separation that it's trying to achieve. In this case, none of those more gradual advisories are sufficient. So here it would tell the plane to climb at 1,500 feet per minute. And again, the sense of that maneuver, whether it's climb or descend, is communicated to the other airplane to make sure that it does the opposite. One other aspect of TCAS that's important is that it can reverse the sense of that advisory. So if one plane starts to say descend, and the intruder airplane does something unexpected, like it also descends for some reason, the algorithm can determine that and switch the sense to tell the plane, okay, this isn't working anymore. You need to, instead of descending now, you need to climb. And it gives a little bit more of an emphatic indication, climb now, to kind of get the pilot to change the sense that they were involved in. So that's the basic idea behind how TCAS works. And it's been extremely effective, a very strong component of what brought that collision rate down that I showed on the first slide of the presentation. There have been a number of cases that have been reported saves due to the system intervening. However, there have been some issues. So there was one accident in 2002 where a Russian passenger jet collided with a cargo aircraft. This was in the middle of the night over southern Germany. And what was especially troubling was that both aircraft had TCAS on board. So obviously, a lot of concern and scrutiny over what was going on and why this happened. And something of a simplification, but this is sort of showing a side view of the two planes. And what happened was there was a very late instruction from an air traffic controller to the Russian pilot to descend. They're starting to get very close, and the air traffic controller told the Russian airplane to descend. And at just about the exact same time that happened, the TCAS unit also triggered a resolution advisory telling the Russian plane to climb and the cargo plane to descend. And the Russian pilots had been trained to follow what air traffic controllers told them and not follow what TCAS told them. And so they actually descended instead of following what TCAS was telling them. The cargo aircraft on the right followed its TCAS RA and descended, and both aircraft basically descended and collided into each other. And so the key question is, why didn't the sense of TCAS reverse in that case? What was going on? And I won't go into the details. It's actually a fascinating story in terms of the algorithm and why it failed in this particular case. But roughly speaking, the algorithm was designed assuming the pilots were going to do what it tells them. And here's obviously a case where they weren't. And so there was a pretty strong response, especially in Europe where the accident happened, first to increase pilot awareness that they need to follow the RA, that the system on board knows more accurately what's going on than the air traffic controller does. It's coordinated with the other aircraft, so they really need to follow what TCAS tells them. It was also identified that these types of events were happening very often, more often than we would really want, many times a year. And so it was a significant enough concern that there was a large effort to make some changes to the algorithm to prevent it from happening again. And so there was a change proposal built to basically make it more likely that TCAS would reverse its sense and prevent that kind of a situation from happening. And so at Lincoln Laboratory, we got involved in this in the early to mid 2000s through a series of modeling and simulation activities to first model all the different components of the airspace, how airplanes fly, run simulations to quantitatively estimate how well TCAS would work, and then from those safety metrics, then make a decision about whether a given change in the algorithm was actually going to be safer than not changing it. And to do that, we used a large number of radars across the country to build an accurate understanding of how aircraft fly around. So this was an effort that began in 2007, pulling data from radars all across the US, building thousands and thousands of flight tracks that we could then use to represent aircraft motion in a statistically accurate way. And we also built other models for other types of aircraft, like unmanned aircraft or gliders and things like that. So this is just a snapshot of what that looked like in terms of different types of aircraft. And where you don't see colors, that's just because at the altitudes I'm showing, there wasn't sufficient radar coverage to get returns of aircraft flying there. But we also, in the bottom left, is showing just areas where aircraft got fairly close together. So that gave us a great set of data to look at how are aircraft behaving when they get close together. And then we can use that in a simulation to evaluate how well TCAS is going to perform. So we built a series of encounter models, they're called, that using all that radar data, we then built a Bayesian model that allows us to represent the probability that an aircraft in a given position is going to, say, turn or climb or change speed. And so from that, we can populate a set of data tables that are representing what we've been observing in the actual airspace, and then randomly sample from those basically to build these synthetic trajectories that we can use in a simulation. So we have the ability then to run millions and millions of encounters on a computer that they're not just arbitrary, they're statistically representative of what's actually happening out in the real world. And we connected that to a simulation capability called CASAT, which basically allows us to run a couple different aircraft against each other with the actual TCAS algorithms or changes to the algorithm and different models on board to look at how well that all works. So this is just an example from one of those simulations, basically replicating what happened in Uberlingen. So that those aircraft had version 7.0 on them. The Russian airplane's on the left again, following air traffic control. So it's going to descend no matter what TCAS says. And the aircraft on the right is going to follow what TCAS tells it to do. And when we run the simulation, the aircraft on the right gets a descend advisory. It actually increases. And in the simulation, you can see they follow that and have that collision. So we're able to replicate the bad things that happen with TCAS and demonstrate that, yes, in fact, there is this vulnerability in the algorithm. And then look at some changes that were made to the algorithm that, yes, in fact, we can validate they do successfully reverse the sense. And even though that airplane on the left is descending, the aircraft on the right gets this reversal to then climb. So that's great. So we get confidence then that this change in the algorithm is effective. The question then is it always going to be effective, or is it just effective in some cases? And could it in fact introduce other vulnerabilities or problems elsewhere? So that requires more of a statistical analysis. So I'm going to just show an example here from some runs we ran where basically we want to compare how far apart are airplanes without any change in the TCAS algorithm, which will be plotting that separation distance along the x-axis, and how far do the planes get if there is a change in the algorithm along the y-axis. So basically, we're going to run a given encounter twice, once with the original version of TCAS and once with this change built in, and see what happens. Does the change make any difference? And if the change doesn't make any difference, the data point will fall on the diagonal because the separation is the same with or without the logic change. But if we have a simulation run that winds up here, for example, where that dot is, that's telling us that with the original TCAS, we would have maybe had a 550-foot separation, but with the logic change, now we're getting about 800-foot separation. So we've made an increase in separation. That's good. If we're below the diagonal, that's bad. We're actually reducing separation. And so what we do is we run these over many cases. We can actually then also pull out cases that we would have had very small separation without the logic change, but grow into larger separations, are basically saves where the logic change has prevented a collision from happening. Down in this red zone is where we don't want to be. That's where we would have had large separation without the change, but for some reason with the change, we've actually now caused a collision. And this bottom left corner in the purple, basically those are going to be collisions that neither system could resolve successfully. So this is one example of some of the data we got, just a scatter plot, and only 0.05% of the time does this logic change actually cause a difference. So it's very rare that it's actually triggered in a sense. But when it is, it almost always increases separation 92% of the time. 22% of the time, it's actually saving the aircraft from a collision, and only 2% of the time is it maybe causing a collision. So there is some risk that it might cause a collision, but that's overwhelmed by the benefit that change provides in terms of preventing collisions. So this was one part of the data that helped lead to a decision to go ahead and mandate that change in the TCAS algorithm. So, so in Europe, for example, starting in 2015, aircraft had to upgrade their TCAS algorithms to this version 7.1 to help prevent that type of an accident from happening again. So again, it's an example of learning from real operations and then making a modification to the system that's been very successful, and there haven't been collisions like that since that change was made. So today, TCAS, like I said, is extremely successful. It's deployed on more than 30,000 aircraft around the world. There hasn't been a mid-air collision with commercial aircraft in the US since the mandate was put out. Roughly speaking, if you consider the risk of a collision between two airplanes where neither plane has TCAS, if you consider that risk 1, if one aircraft has TCAS, that risk is brought down to about 0.1. And if two aircraft have TCAS, it's brought down to about 0.01. So there's sort of an order of magnitude improvement in safety by equipping an aircraft with TCAS. So again, it's been extremely successful. One of the challenges, though, is that it does issue alerts in cases where maybe action isn't required. And that's what you're seeing on the right side here. This is showing New York. And each of these red little posts is a situation in which a TCAS resolution advisory was triggered between aircraft in the New York area. And this is over 6 months. There were 3,000 alerts, and that does not mean that there were 3,000 near collisions in New York. What it does say is that, especially in good weather, when pilots are given visual separation, planes can be flying safely together, close enough together that it basically causes TCAS to issue an advisory when it isn't required. And in fact, the pilots are aware of the other traffic. And so it's essentially a nuisance alert that they're getting. And as we want to get to higher throughput operations and get aircraft to fly safely closer together, that's going to be a problem if the system is issuing nuisance alerts it can lead to the boy who cried wolf syndrome, where pilots begin to ignore the system when they really need it. So that identified the need to maybe make some additional improvements to TCAS. So one issue was reducing nuisance alerts. There's also new surveillance out there. There's automatic dependent surveillance broadcast, ADS-B, which is another surveillance technology that could be leveraged. And also new aircraft types. There's unmanned aircraft, which have different performance characteristics than conventional jet aircraft from the 1980s, when TCAS was sort of originally designed. So there's an interest in building a new version of TCAS, but also to do it in a way that maybe didn't take several decades. And so that led to what's called ACAS X, which I'll just briefly give an overview of. So this was a system that started internally at Lincoln Laboratory with some seed funding, and then the FAA began funding it as a formal program in 2009 with those objectives to both improve safety and reduce the nuisance alerts, to allow reduce separation operations, and sort of help provide better performance for the future. So I'll just quickly go through how ACAS X works and how it's sort of different from TCAS. So one thing that's different is that ACAS X isn't dependent solely on the 1030, 1090 transponder interrogation system that TCAS uses. It does use that, but it can also accept surveillance data from ADS-B or from onboard electro-optical or primary radar systems, say for an unmanned aircraft that might not have a pilot. So there's a surveillance and tracking module that can take in those different types of surveillance sources. It then provides tracks to a threat resolution module, and not only indicates where the aircraft is and where it thinks it's going, but puts basically an uncertainty model on that tracking. So we're not just doing a single straight line projection of where the aircraft are going to go. It's using a probabilistic projection of where the aircraft might go. And having that probabilistic projection allows the system to make a more accurate trade-off between alerting too early or alerting too late, and basically allows us to make a safer system with fewer nuisance alerts. So the guts of it involve a probabilistic model of the trajectories, and then a process to sort of optimize that avoidance action. That processing is done offline, so we do that sort of offline using a high-speed computer. It takes about 10 minutes in this example, and then from that we build this table that basically tells ACAS X what to do in any given particular situation it's exposed to, and it's taking into account those uncertainties when it does that. So I'll just briefly go through how that works. It's built on what's called the Markov decision process, where we basically model different states the airplanes can be in. So these green circles maybe state 1 is the aircraft are at the same altitude, and state 2 is one aircraft is above the other. And from each state, you might be able to say climb or descend. Those are different actions. There's a model, probabilistic model for if you take some action, what's the probability you would change from one state to another. So maybe if I'm at the same altitude and I climb through action A, there's a 90% chance that I will, at the next time increment, be above the other airplane, but maybe there's a 10% chance that other airplane also is climbing, and so we actually sort of stay at the same altitude. So you can sort of model those uncertainties, build in rewards for doing different actions. For example, a collision would have a very negative reward, and we want to basically mathematically optimize the decision we make to give the best payoff, best reward. So the system uses a number of different states. I won't go through all this in detail, but there's also a number of different actions that might be taken to climb or descend at different rates, and different assumptions on how the pilots might act and different reward values. And so all of this was developed and then tested in the mid 2000s into the early 2010s. So what you wind up with is basically a table that says for any given set of states in terms of relative altitudes and distances and climb rates and so on, what are the various values or rewards of doing different actions? And the system will pick whichever action gives the best reward. So I'll show sort of graphically how that works. So there's many dimensions to this problem. We're going to just simplify it here to two, basically how far above or below you are from an intruder, which is shown on the y-axis, and then how far away you are in time from, say, a direct collision on the x-axis. And this is going to be fixed to the intruder airplane. So we'll pretend that the intruder airplane is this red square here, and we're moving basically from left to right along this plot as we get closer in time. And if we enter this red square, we've had a collision. If we wind up in these green squares, that means we've gone above or below it and have avoided a collision. So what we can do is zoom in and say, take a look at this state where we're maybe 1 second or one set of time steps away from a collision, and decide, should we climb, do nothing, or descend? And use the probabilistic models we've been able to build from all that radar data and look at, if we climb, we have some probability we'll go above, but maybe some probability we'll still crash. And so we can do that for different outcomes. So here's what happens if we don't do anything. Here's what happens if we descend. And based on that, we can then sort of build out for each time step what the best thing to do is, whether it's to climb or descend, and then back up through time and build up this table in that way using dynamic programming. And so it's an efficient way to sort of fill out that whole state space in terms of what maneuvers you might want to do based on whether you're above or below an intruder, whether you should climb or descend. So this is sort of what that looks like in terms of mapping it out. If I have an intruder aircraft, again, stuck here, and I have an airplane that's flying a few hundred feet below it, 20 seconds away, ACAS X is going to tell that airplane to descend if it's in this blue area. If it was in the green area, it would be climbing, or be told to climb. And one of the really neat things here is this kind of wedge in the middle is telling you that if you're flying towards somebody and at the same altitude, ACAS X will actually wait a little while to try to figure out what's really best to get more information about what that intruder aircraft is doing before at some point it says, okay, we got a fish or cut bait now and either climb or descend. And then again, if we were, say, climbing, that plot changes, and somewhere in this blue region again, even though I'm climbing, the system is going to tell me I better stop my climb and descend. But if I get into the green area, I'm going to be told to continue my climb, basically to cross through the altitude of that intruder. So that was all developed through a large number of simulations. There was also some flight testing that I'll just briefly talk about, but the results of at least the modeling were that ACAS X provides about a 20% improvement in safety relative to TCAS 7.1. So it makes things safer. And importantly, it cuts the rates of alarms down by about 2/3. So far fewer nuisance alerts while still providing, even more safe operation. So that's all very positive for the future system. But it was important to validate that through flight testing. So there were a series of flight tests to ensure that the computer models were aligned with what actually happens with aircraft. And these involve both conventional manned aircraft as well as a series of simulations with unmanned aircraft. And I'll just show one example of one of the unmanned aircraft simulations. So this was done with NASA and a number of other partners. This is showing their AIAA aircraft, which is basically a Predator class unmanned aircraft with a manned intruder airplane. In the bottom right, you can see the traffic display that shows the unmanned aircraft here in this triangle, and the intruders coming in as this blue wedge. There's sort of an inset here showing an expanded top view. And what ACAS X is doing is this yellow band is basically indicating that if you continue on headings in this range, it's likely you're going to have a more serious traffic conflict with that airplane. So it's continuing to monitor the situation. And as we get closer, it's becoming clear that there's sort of less and less maneuvering room for us. And at some point, when it gets close enough, ACAS X will then issue a recommendation here to turn right to a heading 115, for example. And in this case, we're going to allow the planes to continue straight because, again, we want to really just validate that the timing of these events are happening according to the computer model. So we actually don't have the unmanned aircraft turn just yet. And then when we get to this red point now, that does initiate a maneuver, and then the unmanned aircraft will start to turn to follow that advisory. So we ran through a large number of flight scenarios like this to validate the computer models to again build that confidence that that the system was going to operate as designed. So just to close, so ACAS X is sort of the next generation of collision avoidance, and there's a number of variants of it that have been developed. ACAS X-A is for manned aircraft, and it operates very similarly to TCAS in the sense that it will track transponder-equipped aircraft and other TCAS-equipped aircraft, but it will not track aircraft that maybe don't have a transponder. It still needs that transponder message. There's another variant, ACAS XU, that's designed for large unmanned aircraft that has the functionality of ACAS XA, but also allows the use of a primary radar on the aircraft, for example, that could detect non-transponding aircraft. And it also allows for lateral left-right maneuvers in addition to the climb-descend that TCAS and ACAS XA do. And then there's another variant for small unmanned aircraft called ACAS SXU, and that could actually be running on the ground through a computer on the ground because the smaller UAS may not have the ability to carry the processing to run the algorithm. So this might be a system that runs on the ground and then uplinks maneuver commands to the small UAS based on other surveillance data. And then the final variant is called ACAS XR, which is designed for rotorcraft. So here you not only can turn left, right, and go up and down, but you can also change your velocity, maybe go into a hover. So that system has even more maneuvering capability and is a potential solution for the urban air mobility problem where you've got, say, vertical takeoff and landing aircraft flying around. So that's a quick run through some of the history of the development of TCAS, some of the changes that were made along the way, and sort of where we're going next with ACAS X. Again, I just really want to point out this involved a number of organizations, many dozens of people working really hard to build that surveillance technology, the threat logic, to do all the safety assessment and build the safety case involving partnerships between the FAA and industry and academia, working internationally to get approval for that, flight testing and so on. And we're really excited about this next version of TCAS called ACAS X that allows even more safety and fewer nuisance alerts and opens up really the world for all these new types of aircraft that are coming along. So with that, I'm happy to answer any questions.
Thanks, Dr. Kuchar. There's 3 questions from Tom Stagriano. So I'll read out the first one. So is TCAS or ACAS X, I guess, are they cost effective for near-term use by commercial UAVs, UAMs, and other new type of aircraft that's coming into urban air taxi type applications? Right,
yeah, so I mean, that was one of the critical, going back a little bit to the development of TCAS itself, was the need to make a system that is both effective and also makes an economic case, for aircraft, especially, airlines or general aviation users, to put this equipment on their aircraft. It has to be economical and make that case. So the original design of TCAS was deliberately built around the same surveillance technology that aircraft were already equipping with the transponders, so that you would have to put a TCAS unit on board to get the collision avoidance protection for your own pilot, but all those other airplanes out there didn't need to sort of put equipment on them in order to allow this collision avoidance capability to be effective. So now when we get to new operations like unmanned aircraft, urban air mobility, there's going to be the same issues, right? That these are going to be aircraft that have maybe very tight cost margins. They might be limited in terms of size, weight, and power of equipment. And that's where ACAS SXU could come in, that it might be a service provided by a UAS traffic manager, sort of a centralized service that provides that collision avoidance capability to the small unmanned aircraft without requiring those small unmanned aircraft to actually put any equipment on board themselves. So from that standpoint, it could be very cost effective. For urban air mobility, there, I think we have yet to see sort of as those vehicles mature and we understand more how they're going to be operating in terms of what their maneuverability is and so on, how to get these systems on. But I mean, in general, the technology for ACAS X is fairly low cost. It's basically just some processing that would use some surveillance information that might be provided by a transponder system.
Thank you. The next question again from Tom. In a way, you already answered this. So has there been any instances where third aircraft has involved? So maybe give a twist to this, that how many aircrafts can TCAS, or I think in this case, ACAS X can handle in an instance?
Yeah, no, that's a great question. So, and TCAS was designed in sort of a pairwise sense that it will sort of treat each intruder separately, come up with a solution, but it will look at more than one aircraft at a time and figure out what solution is sort of the best of alternatives, given all the different aircraft that are out there. So one of the good things is that the probability of 3 aircraft coming into a close encounter is much smaller than the probability of 2 aircraft, and the probability of 4 aircraft is even much smaller. So those probabilities help allay some of the risk. Both systems, TCAS and ACAS X, aren't coming up with sort of global solutions for all the aircraft, sort of considering them all as a bunch. They're sort of doing piecewise solutions, which again, through the modeling and simulation we've been able to run, we do run those multi-vehicle cases and still able to show that the system performs well. So there haven't been any multi-aircraft collisions operationally. There have been events where aircraft have gotten close together where there's been more than 2, but they're extremely rare. But for things like small UAS and urban air mobility, again, where we can anticipate a much higher density of traffic, that's going to be a very important consideration. So that's one of the areas that we're still looking at with ACAS SXU, for example.
Okay, thank you. Next question is TCAS or ACAS X, is there any limit or only useful when certain altitude above terrain and away from nearby mountains and tall buildings or towers? Is there any change in efficacy from those effects?
Yeah, so you don't want to be telling a pilot to descend into a mountain, right? So TCAS does inhibit a descent advisory below a certain altitude. So as you get lower and as you get in towards an airplane, it becomes less sensitive and will not trigger a descent advisory. And also just to help avoid nuisance alerts again, as you get closer to an airport at low altitudes where there might be other traffic on the ground, for example, you don't want to be issuing a collision avoidance advisory against a plane that's holding short of the runway. So it does have algorithms in there to deal with terrain or altitude. And that's another area we're looking at with ACAS SXU is also providing terrain collision avoidance using sort of the same foundation as the aircraft-to-aircraft collision avoidance. So you can essentially treat the terrain, if you have a terrain database, you could treat the terrain as yet another intruder essentially and come up with solutions that will avoid the terrain as well as other traffic.
Okay, thank you. Next question is from Mohammed. What will happen if one aircraft uses GPS altitude and the other uses barometric altitude? And how will TCAS determine the correct relationship between those 2 altitudes if there's a situation that, say, barometric altitudes is not correctly calibrated?
Yeah, no, that's a great question because aircraft fly off of barometric altitude, at least conventional aircraft. And it's the barometric altitude that's encoded in the transponder message. So TCAS entirely relies on barometric altitude, doesn't use GPS altitude at all. Now, when you get to, say, UAS that are using GPS positioning and altitude, this is where your UAS traffic management system might have to come into play to ensure that either everybody's using the same GPS altitude reference or is converting a GPS altitude into a barometric altitude given the barometric pressure. So that's something that will need to be addressed when you're starting to deal with mixed altitude sources. But at least right now, TCAS and ACAS XA are just using barometric altitude.
Thank you. Next question is from Rob Leonard. Is there a timeline for ACAS X implementation in large transport aircrafts?
Yeah, a great question. So the US standards for ACAS XA have been approved. I don't recall the year, but it was a year or two ago. And there's still discussions internationally about getting approval for ACAS XA. So I think there may yet be another year or two before there's international acceptance. It really requires international acceptance because planes fly internationally. So if a domestic aircraft were to equip with ACAS X, you'd want it to be accepted internationally. So we anticipate that deployment, it could happen in the US today, and there have been some planes flying around for operational evaluations with ACAS XA, but it's really going to require that international adoption in the next couple of years before it could be more fully deployed.
Okay, thank you. Next one is Thomas Interman. I think he had the same question, and that one. The one after that looks like the last question is from Zachariah Ola. So he said, you mentioned that the MDP or Markov decision process is solved offline and lookup table is generated. Is there a use for solving the MDP online if an aircraft is exhibiting an actuator fault and lookup table might no longer provide a safe advisory?
Yeah, that's a great question. So, it depends on sort of the computational power that you can put into an avionics box on an aircraft. And the focus for ACAS X was to make it as sort of backward compatible as possible with current TCAS. And so that meant having something that would work with relatively low performance computational power on an airplane, which lends itself to a lookup table essentially. So it would require a fair amount more computational power to be solving MDPs online in a real-time sense. Not impossible, and we have looked at sort of online types of solvers for that kind of a problem. But one potential solution is if you do know that there are certain failure modes, you can build those in again to the lookup table so that you might have a different table for a given performance issue. For example, if you have an engine out and that affects your climb performance, there might be a need to have a different table to handle that situation so that you're getting an advisory appropriate to the aircraft capability. Ideally, yeah, it'd be great to do that online, but I think practically speaking, at least in the near term, that's going to be hard to do.
Okay, thanks, Dr. Kuchar. I think that'll be, I think the time is almost perfectly timed up. So we'll wrap up the presentation. So thank you very much, Dr. Kuchar, for a very insightful presentation. I hope everyone enjoyed it, and have a great evening, everyone. Good night.
My pleasure. Thanks a lot. Take care, everybody. Bye-bye.
Bye now.